Okay, so there's a typo here. The vector field, the z component of the vector field should be 2y. So what I want to do is try to find a scalar potential of f. In other words, a function, a scalar valued function whose gradient is equal to f. And I want to tell you before I do it that we can't find one. And we're going to see what happens when we try to find a potential for a vector field that does not have a potential. So we're going to start by assuming that there is a potential. In other words, we're going to start by assuming that there is a function that satisfies the following equations. Its x derivative is equal to e to the power of x plus y. Its y derivative is equal to e to the power of x plus y plus z, and its z derivative is equal to 2y. Okay, so we're going to, like I said, we're assuming that we can solve these equations. We can solve these three differential equations. We're going to show that there's a contradiction. We're going to show that this assumption that there is a solution leads to a contradiction, and that will mean that there is no potential that satisfies these equations. For those of you who are taking the proofs class, this is kind of like a proof by contradiction. The logic is the same, but we're not going to be as rigorous as you would need to be in one of these classes, in one of your proof classes. Okay, so if the x derivative is equal to e to the x plus y, so the first two steps are going to be exactly like the previous problem. So the x derivative of f is equal to e to the x plus y. This means f of x, y, z is going to be the antiderivative of e to the x plus y, plus a constant that is just a function. So when we say a constant, we mean that it is a constant with respect to x. So in other words, is a function of y and z alone. Okay, now we're going to use the y derivative information. So we know the y derivative is equal to e to the y plus e to the x plus y plus z. So that means that the y derivative, e to the x plus y plus z, is equal to the y derivative of this function. And the y derivative of this function is e to the x plus y plus the partial derivative of g with respect to y. And so this tells us that the partial derivative of g with respect to y is z. And so g of yz is equal to yz plus some unknown function of z alone. Okay, this is exactly, so far this is exactly like what we saw in the previous example. Okay, but now look at what's going to happen. So we know that we're assuming that the z derivative of f is equal to 2y. So this tells us that 2y is equal to the y derivative of g. What is the y derivative of g? Let me say that again. We're assuming that there's a function whose z derivative is equal to 2y and satisfies all this other stuff. So we know that 2y is equal to the z derivative of g. What is the z derivative of g? Well, it's y plus h prime of z. Now notice what happens. Now we have that h prime of z is equal to y. Now this is the problem because h is a function of z alone. It does not depend on y, which means its derivative does not depend on y. If a function doesn't depend on y, its derivative can't depend on y. But now we're saying h prime of z is equal to y. And now this is a problem because h of z is only a function of y. So this is the contradiction. So there is no potential. So there is no potential. Okay, now I'm going to say something that if you don't care, you can stop listening for a few seconds. We've assumed several things. One, we've assumed that there's a potential. We've also assumed that we can integrate these functions. So one of those assumptions is wrong. Either that there is a potential or that we can do integrations and stuff like that we need to do, that we can take derivatives in the way that we need to. One of those assumptions is wrong. In this class, it's always going to be that we can take derivatives and integrals like we need to, unless it's explicitly said otherwise. So then the only assumption that's left is that a potential exists. Okay, so since there's a contradiction, there is no potential. So assuming that a potential existed led to a contradiction, therefore no potential can exist. Let me just go over one other thing. So notice, let's compute the curl of this vector field. Okay, so e to the x plus y is the first component. I think e to the x plus y plus z is the next component. And 2y is a third component, and I just realized I made a mistake. I did the exact thing that I told you not to do a few videos ago. That's sort of the pattern of how these things go with me, isn't it? Okay. I need to put the differential operators here. This is e to the x plus y. This is e to the x plus y plus z. And then this is 2y. Okay. So the first component is going to be the y derivative of 2y minus the z derivative of e to the xy plus c. So this is going to be 2 minus 1. The next component is going to be minus the x derivative of 2y, which is 0, minus the z derivative of e to the x plus y, which is also 0. And the third component is going to be the x derivative of e to the x plus y plus z. That's e to the x plus y minus the y derivative of e to the x plus y. And this is equal to 1, 0, 0. In other words, the curl of this vector field is not equal to 0. But let's go back up to this fact here that we saw. If the curl, so this is the fact that I'm referring to, or let me get everything. Okay, so the curl of the vector field is not equal to 0. That means that f is not a gradient field. In other words, there is no scalar valued f such that f is equal to the gradient of that function. So that's another way that we could show that no potential exists. One way that we could show what a potential doesn't exist is to go through this process that we did here, show that it leads to a contradiction, so no potential can exist. Another way is just to compute the curl. If the curl is not equal to 0, then a potential does not exist. Now, it's actually true, though, in a qualified way. As Dr. Yaskin says in his book, for 99% of the time, if the curl of a vector field is equal to 0, then there's a potential. But there's important cases where that's not true, cases where the domain has a hole. Now, we don't really care about those domains in this class, but I just wanted to point that out to you.